Hello and welcome to this video lecture series. You have the link to this repository, but you can just directly go here and get access to the repository. Here you will find all the notebooks, and also I will upload the videos here, and you can just follow from the beginning. To use the Jupyter notebooks, you should first download this repository to your local machine. You can download it just by clicking here and download zip, or you can just copy it and use git clone and this link, and you'll have all the necessary files. Since I already have them, I'm not executing this line, but when you have everything, you can just install Jupyter Notebook, then execute this line of code, and it should start the Jupyter Notebook. So here we will have all the notebooks that we will use in the series. So we will start with the review notebook to refresh our memories. We will start our review by looking at single qubit gates and how we use the matrix notation in quantum computing. So we have a 0 and a 1 state in quantum mechanics. We usually denote this state with either the 0 or up in the z direction. In the matrix form, the 0 cat becomes a 1-0 matrix, a two-element one-dimensional matrix, or a vector you can say, and our 1 cat is also shown as either a down spin in the z direction or with this 0-1 matrix. We already defined the other directions, other matrices using a similar notation. We denote the plus state with up in x direction, and it was a superposition of 0 and 1 states. And similarly, we defined the minus states and also up state in y and the down state in y. So you can just check these things and refresh your memories. We also had some single qubit gates, and the simplest one and the one that we know from classical computing was the X gate, or you can call it the NOT gate. X gate takes 0 state to 1 and takes 1 state to 0, and in matrix form you can see it here. Z gate is also a simple gate. It takes the 0 state to 0 and 1 state to 1, but with a minus sign in front of it. This was because the 0 and the 1 states was the eigenvectors of the Z gate, and the values in front of them were the eigenvalues. Since these states are also our basis states, you see that this Z gate is a diagonal matrix, and it also has eigenvalues stored here for the 0 state and -1 here for the 1 state. Following the same logic with X and Z gates, we have the Y gate, which is in fact the Y, Pauli Y matrix, and actually all the X and Z gates were also Pauli gates, and it is defined like this, following a similar logic. So here you can see a short summary of what these gates are doing, but let's remind ourselves that these gates, all of them has different eigenvectors, but they all have the eigenvalues of +1 and -1. So 0 and 1 state was eigenvectors of Z, so you see that we have plus minus here. For the X gate, the eigenvectors are the plus and minus states, and plus state was up state in X direction, minus was down in X direction, and you see that we get the eigenvectors and eigenvalues. Similarly, for the Y gate, we have up, down, and the eigenvalues. Another important gate was the Hadamard gate that we usually use to create superposition, and And when you apply Hadamard to the 0 state, you obtain the plus state, and when you apply it to the 1 state, you obtain the minus state. RY gate is an important gate that we usually use in practice, but something that is usually not mentioned in the earlier parts of quantum computing theory. It's a rotation gate about the y-axis. It takes the state and rotates it around the y-axis to get a new state. Following the same logic, we also have the Rx and Rz gates that rotates them about x and z-axis. Heading up to Ry gate, we have the U3 gate, which is a generalization of rotations in 3 dimensions. Since our states are complex, although that they have just 2 elements, since they're complex, they are expressed in 3 dimensions using the Bloch sphere. And since all the transformations in quantum mechanics are unitary transformations, we can express all the gates with rotations. And since also we can express all the rotations with the U3 gate, any transformation can be expressed using this U3 gate. As you see here, it only takes 3 parameters, and the matrix representation is like this. And you can see that when we put lambda and phi to 0, we obtain the Ry gate that we just saw. And as an example, we can just use the right parameters to obtain any gate, as you see here in the Hadamard case. We also have 2 qubit gates, which are really important when introducing correlations between qubits. So the CNAP gate is the most famous one, and the one probably used the most. And the matrix representation was like this, and it was controlling the first qubit here. And if the leftmost qubit is 1, it would apply a NOT gate to the second one. And you see that only this 1, 0 and 1, 1 states are getting affected by this controlled NOT gate. We also have controlled unitary gates following the same logic, replacing the NOT with another gate. And this allows us to implement controlled rotations or controlled any unitary operation. Combining the CNAP gate with multiple qubits, we can obtain multiple qubit gates that are useful in many quantum algorithms. You probably saw some examples, but I will try to keep it short here. If you want to read more about the theory, you can refer to these references, which you probably know, but these are good resources that you can access freely and will benefit from a lot. So let's continue to our second notebook.